account, the traditional way to do computer vision was really this, where you would send the whole image into the neural network and just let the neural network do its stuff, right? So if I have a 28 by 28 image, that's totally 784 pixel. So now each pixel is a feature, right? And traditionally, what would happen inside the neural network is it's just finding the relationship between one pixel to another pixel, right? So it's just trying to find out how a particular pixel is related to every other pixel within the image, right? That's the idea behind ANN. When I give all the input features, let us say there's a position 1 comma 1 in an image. Okay, so now this is my image. I have this position with the pixel value 200 and then another pixel value 214, pixel value 0, 15, 25, 40, 40, 20, 0. So what ANN basically does is by making this fully connected network, it is seeing how this pixel value is related to every other value within the image, right? And it's trying to find that relationship. That's what ANN is uh, imagined to do, right? Now, the core of computer vision that people had relied on till now was basically this idea that an image actually has patterns, right? So ideally, what traditional computer vision would do is for the same pixel arrangement that we discussed here, which is 220, 0, 40, 214, 0, again 40, 15, 25. So we are in traditional computer vision, we would try to see if this diagonal which you see here, this diagonal of bright pixels, you know, does that, or let's just make it 225 for convenience. Okay. This diagonal of bright pixels, does it have any meaning in representing the image, right? That's the thought process behind using convolutions. So you would you'd make like right edge filter and then a horizontal filter and then a vertical filter and see how to combine these two filters in order to make this diagonal. That was what you imagine when you do convolutions. But in artificial neural network, you are giving every image as an input feature. So your idea in artificial neural network has slightly changed, where you are saying, how does this number 200, how is it connected or how is it related to the other numbers in the image? So you are basically seeing how are the bright portions of the image related to the dark portions of an image, right? Because if everything is bright, you're just going to have a like a white screen or like a white image, which doesn't make a lot of sense. If everything is black, again that doesn't make any sense either. It is a systematic variation between the bright and dark regions which actually define the features, right? So in ANNs, that's basically what we are trying to do. We're trying to see how each bright pixel is related to every other pixel within the image, right? Using our dense connections. So these are actually two parallel approaches to here. Like using convolutions, people are trying to create filters and people are trying to combine them and trying to build a model. And on the other hand, people are just saying, let's not worry about these convolution and all that. Let's just see if we can find a relationship between the bright regions and the dark regions. Because if it's just plain white, white noise, all the pixels are scattered randomly, then obviously there's not going to be any systematic variation, systematic relationship between the bright regions and the dark regions, and it will emerge in the neural net. Now these are two parallel approaches. Um, and every year, people really wanted to do. There used to be this competition called ImageNet. I mean, it has a big name. I'm not going to go into a big name. International something for images computer vision. So there is this ImageNet data set. There is a data set called ImageNet, which has like millions of images, all labeled, differently actually. So you'll have like mammals, you'll have carnivore, canine dog, working dog, like different labels for different images. And the job, the goal of the competition every year was that people would come up with their own algorithm and they would present it in this conference and say, okay, now last year's best performance model was had an accuracy of 35%. This year we have improved it to 38%. And then the next year it would be 41% and all that. Okay. So people from all over the world would present their algorithm in this conference, and the name of the challenge is this ImageNet Large Scale Visual Recognition Challenge. So people would classify images, and detection was also part of the competition. So there are around 20,000 categories of images, and now a lot of images within a category. 14 million annotated images. So the ImageNet is basically a huge, humongous data set of images, basically like this. So you can see, these are dogs, some are hyenas, some are working dogs, some are huskies. So the granularity of the classification is very different, but it has a lot of images. And the goal was to give make a prediction which would be among the top five. So, for example, the leopard, and it is success if leopard is within the top five predictions. So there is a leopard prediction, jaguar, cheetah, uh, um, snow leopard, and Egyptian cat, right? So the top prediction is leopard. Here we are finding that this is agaric, and then there's mushroom. Mushroom is the correct answer, but it is still considered correct because it is within the top five. There were different, different categories: top 5%, top 1%, top 10. We're not going to the details of that. Um, I guess this is supposed to be Sherry, but this is classified as Dalmatian. That's why this is incorrect. But that was the goal of this competition. Okay. So year on year, the error rate kept on coming down. So in 2010, the error rate was 28 some percent. 2011, it was 26%. And between 2011 and 2012, there was a sudden drop of nearly 12%. Okay. Now, in the machine learning, in the computer vision world, that's huge. Because what happened before that was, in traditional ML, people would come up with all these very complicated filters. So they would come up with a filter which would find a particular feature in the image. Like for example, like as we discussed in the last session, people really started with edge filtering, and then there is there's a score for each of this, and then come up with a different filter which measures different size, I mean different shapes, and then give a score, and then build a machine learning model. That was basically the approach. So it had a lot of pros in the sense that it was traceable, people were able to really explain what they did, and they really said, okay, this year I came up with a filter which will do this job, and that's why the accuracy increased or the error rate fell. But the whole field of computer vision was basically expert driven. So you have an input image where, and then feature extraction was really manual, and then you would use like a classification algorithm. Now this classification algorithm, it can be a traditional ML, or it could be a neural network. That is a different thing. But the feature extraction was always manual, right? So it had too much stress on mathematics. It was very highly academic. Neuroscience, psychology, all this played a role. So people will say, people will conduct experiments in phase perception, and then they would say, oh, no, if I'm going to blank out the eyes, then face recognition really becomes difficult. So whatever image we have, eyes are very important for face recognition. This paper would come out in probably neuroscience, perceptual neuroscience, or psychology, cognitive psychology. And then the mathematicians would go behind that, and then they would find how can I really model the eye, right? And that would be given to the machine learning experts, where they would say, okay, now I'm going to come up with an I score, and I'm going to build an SVM or an ANN, or do something which will actually do the classification task. This was the field until 2011, right? But in 2012, there was this huge drop in the error rate because of this architecture called AlexNet, right? And that's really when deep learning really emerged, and that was kind of revolutionary. And it is still very, very important from a historical perspective. Um, uh, okay, the goal of the session would be to see how AlexNet kind of won, what it did differently, um, uh, than the previous architectures, than the existing architectures, which really made it successful. Okay, and again, there's no suspense here since the course's module is called deep learning and its variants. Um, they did implement the deep learning. Uh, but I would want to make one clarification here. It's not that ANNs did not exist before 2012. Uh, ANNs existed, but their approach was largely this. Okay. Now, the problem with this is this works for a 28 by 28 image, right? 784 input pixels. Let us take an image which is 256 by, which is 256 by 256. So for a 256 image, how many input features should you feed into the ANN? How many input features? Can somebody do the math?
256 squared?
Exactly, yeah. So what is the exact number?
65,536.
Thank you. 65,536.
36. Yeah.
Right? 65,536.
Yeah.
Now, this is a 256. Remember, last week we saw what RGB images, right? So it's 256 times 3. Why? Because there is a red channel, there is a green channel, and there is a blue channel. So it is 3 times 65,536. What is the number?
196608.
Right? These many input features. Right? So computationally, it becomes a nightmare. And if you want to do batch normalization, or if you want to do a batch stochastic gradient, remember, if my batch size is going to be 32 or even 10, okay, it is going to look at 10 images at a time to do all the math that we have discussed in neural networks. Forward propagation, back propagation, weight updates, the learning rate, doing the differentiation, delta W by delta output by delta W, doing all the chain rule, right? That is a humongous amount of math. Okay, so as good as ANNs are for small images, at scale, ANNs do not really work well. Now you might ask, why should I use a 256 image? Right? Why can't I just use a smaller version of the image? Right? Why can't I use a 100 by 100 image? I'll still be dealing with enormous numbers, but it is not that much, right? So 100 by 100 is 10,000 input features times 3 is 30,000. Which is still doable, right? And image resizing is not a big deal. I can just, whatever image I have, instead of reducing it to 256 by 256, I can reduce it to something that the neural network can handle. If it can handle 100 by 100, do 100 by 100. If it can handle 200, give 200. 50, just give 50. Now, what is the problem with that approach?
The quality of the image will not be that good.
Correct. So, once we reduce the size of the image, you would have noticed that the quality of the image drops. Now, for again, it is task dependent, right? If your job is to find if there is a face in the image or there is no face in the image. I'll slightly sidetrack here because I know being DBA, I don't want to spend a lot of time in the architecture and parameters and all that. But as a business case, you see, traditionally, computer vision it did not evolve to find out if the image is a cat or dog. Today, if we take computer vision, the first example that we come up with is it a cat image or a dog image? Right? That's because it's favorite. Everybody knows cats. They are pets. They are cute. Easy to relate, right? But a lot of computer vision problems started on a very serious note. Like, for example, security. Let us say that there is a camera in a high secure vault or something, and you want to find if there is a human in the room or not, right? So, this is a very specific problem. And there are a lot of things that you can really control. Like, for example, if there's a door or something, you can fix the camera in which you can fix the camera so that only one profile of the person will be captured, right? Imagine a room, a high secure room, where you install one camera and there's only one door. So the person who comes into the room will have only one profile. Like there's no side profile, there's no like only forehead and all that. So a lot of computer vision problems evolved to make sense of a very specific problem, which is also actually easy to, not really easy, um, um, but again very specific. Like for example, there's a human in the room or there's no human in the room, right? So the failure point there is not to is not if it misses a dog or anything, right? But if it can find a human and classify the image as human, not human, that is good enough, right? And the input would be mostly very what to say controlled, right? That's how traditional computer vision things evolve. Again, today we take cat and dog as example, but if you look at all the papers in the past, they really did not care about cats and dogs. They cared more about there is a face in the image or there is no face in the image, right? which is actually a security thing, because that's why you want to solve a problem, not for fun. Because all these computations, all these resources, they should make sense for investment. Coming back to the session, if I reduce an image quality from my required dimension, from my required size to any size that will work for the neural network, I'm compromising the quality, right? Even if I'm going to compromise the quality, some of these things, since they are security tied, if the algorithm is dependent on detecting the eye, for example, like the frontal position of the eye, right? The algorithm might actually fail. It did not fail because it didn't detect the eye. It failed because the most important feature was not captured because of the image resolution, right? So the image resolution becomes important. Why? Because the algorithm running in the background is dependent on some of the features with a few assumptions that the eye will be captured, the ear will be captured, nose will be captured, because people are engineering these things manually, right? That is a very important distinction that we would want to make between the traditional problems that computer vision solved and the modern fun kind of problems which we use computer vision for, right? So reducing the input size is not always an option, right? Because we want certain features to be captured, which the algorithm is heavily relying on, right? So we can't just arbitrarily reduce a 256 image to 100 by image just because a neural network is able to handle it, right? So I hope I have made the problem clear. Now we'll come to the solution, right? So progressively
Professor,
from, yeah,
it's Leon, and
yeah.
could I give an example? I know at the end of the last class I had talked a little bit about a real world example of what you were just talking about, the image and the importance of the detail in the image.
Mhm,
And in our workplace, we are a fleet company. We have about 3,000 pieces of equipment that drive. And we have put a machine learning, artificial intelligence solution in our trucks.
mhm,
That equipment watches for eye movement as
mhm,
they're driving and any distractions that may come into the driver's purview.
mhm,
And it tracks that, and it has helped improve our driving performance
mhm,
as an organization. In particular, it watches for handheld devices, cell phones, and
mhm,
or eye movement away from the position that the eyes should be in when the driver is driving. So this
mhm,
technology is in real time and
mhm,
is flexible in that sometimes there are issues that the algorithms are not looking for. And one in particular, we work with the company for railroad crossings. It did not recognize railroad crossings that were not regulated, meaning
mhm,
there's no stoplights or arms coming down.
mhm,
And
mhm,
so we work with them to write a new algorithm to recognize the shape of the sign of a railroad crossing, because we
mhm.
want all of our trucks to stop regardless of whether it's regulated or not. So that's a real world example that we use in our company every day and has been significant in improving our safety performance as an organization.
Yeah, great. So if you come back to the problem, actually, uh, we will, yeah, Yeah, so a lot of things are running in mind, like what could be the data set, what is the labels, or is it a classification problem, or is it an object detection problem? Because you see, this can be solved in a number of ways. We will probably take it up at the end of the session. We will try to solve this as a classification problem and probably as also some sort of an object detection problem, and see which one would be more efficient of the two. Does that make sense?
Yes.
Yeah, sure. Okay. So what basically
Doctor, sorry, one query also, please. Is it this? Is this the same? How can I say? It's the same algorithm used for the phone recognition when you unlock the
yeah.
phone, and also the gates. For example, in our company, also the gates are opened by the face. When you put put your face on the camera, the gate is open. Is it the same algorithm used?
Yes, yes. So all the face recognition detection. So
Yes.
face recognition, yes. It's a computer vision, it's a core computer vision problem, right? So what really defines your face is basically everybody has eyes, nose, mouth, right? There's a common arrangement, right? But what differentiates one face from the other is the subtle difference between the nose, or between the eyes, between the eyebrows, and the features of the face overall. So yeah, all these algorithms are trained to pick up those features. Yes.
Thank you.
Okay, so I'll not go into the convolutions again since we have done it already. Did we do this last class? Not this, but some version of this. Let us say there is an image and there is a filter. And if I'm going to convolve this filter with this image, I would start with 1 times 1, 1 times 0, 1 times 1. Where are these numbers coming from? This one is this one, right? This 0 is coming from here. This is coming from here. Okay. And 0 times 0 plus 1 times 1, 0. So I would do this and then I would basically do I would sum all these and I would come up with a number, and this would be my convolved feature. We did some version of this last week, I hope, right? Using our edge filtering demo.
We did with the Excel sheet, yes, folks.
Yes, so we did with the Excel sheet. So I'm not going to explain this. So the image, this is called the filter or the kernel. I'm going to use these terms interchangeably, and I'm not going to worry about people who say there is some small difference between filter and kernel. I'm not going to take that seriously. I'm going to use this interchangeably, filter and kernel, image, and what I get after the convolution operation is what's called the convolved feature, right? So convolved feature is this, and I'm going to give a few moments to look at this and understand what's going on. If you're good, we can continue. Like how we got the convolved feature from the image.
Sorry, how can you come up with number 4 again?
Which number 4? The first number 4?
Yeah, the first number 4. So 1 times 0, 1 times 1
Plus?
Oh, plus the whole thing.
Yeah.
Got it. So you like condense it to this.
Yeah. No, we can.
And then the next one would be the second row. Got it. And then
So
the
I'm going
next
to
one would be
slide
the
it.
part. Got it.
I'm going to slide it along the columns. And once I'm done, I'm going to come down and I'm going to do it for the whole image. Okay. This operation, the sliding thing that's going on the screen, you're going to remember that and we are going to visit this multiple times. So it's very important that we understand how this happens. Are we good?
Yes, yes.
Okay. Again, we discussed this last session. Okay. So what we are going to do here next is, and I think I gave a small introduction to this. We are going to combine the power of convolution with the power of artificial neural network. So we are going to, instead of initializing single nodes in the hidden layer, I am going to initialize a filter with some specific dimensions. Let us say 3 by 3, 5 by 5, 11 by 11, whatever. And I'm going to retain the power of neural networks, right? So instead of a single node, it is now going to be a filter, right? So when instead of 15 neurons, I'm going to say 15 filters. So I have 15 of these going on inside my first hidden layer. And when the neural network initializes, it's going to start with random numbers within each of these. Okay. And it's going to go through the image similar to what we have done here. If this is my original image, okay, this is my image, and this is my filter. I'm going to start with random numbers, and it's going to convolve this part, and then move to second, and then that's going to keep happening. And it is going to make a prediction. Let us say it is a cat or a dog prediction. Obviously, since these are random numbers, it's not going to make a good prediction, so the error is going to be high. Okay, and then back propagation happens. And weight update. Now, when I say weight update, here weight update was at the level of this node, right? But here, when I'm using filters as nodes or as neurons, remember there are 9 filters going on, 9 values here, right? So this is my weight 1, weight 2, weight 3, like that I have weight 9. Okay, now back propagation and then there is a weight update. Remember now every weight is going to be updated accordingly. Okay, again it's going to make again there's going to be a forward pass. Is going to make a prediction. Forward pass and then a prediction. Again there's going to be some high error. Again back propagation, weight update. But here again the weight is not a single weight that's updated. It is this combination of numbers that's going to get updated. Okay, like this, it's going to do for multiple images, multiple like thousands of images and I mean, depending on your batch size and all that, n number of iterations is going to happen, right? Our hope is at the end of it, it's going to come up with some set of meaningful numbers, probably something like this, which will detect vertical edges. Like one of the filters will do this, right? And then remember, we are initializing multiple filters here, right? So while one filter is doing this job, filter one, there's going to be another filter sitting somewhere within the neural network, which is going to do a different kind of detection. Okay, that will probably do all the horizontal edges. Right? Now, if we go deeper, now my F1 and F2 are in my hidden layer 1. Okay? Let us say I have a hidden layer 2. Now these two filters, which are basically horizontal and edge filter, they will somehow combine to give me a filter that is this shape. Okay? Probably I'm going to make it 1, 1, 1, minus 1, 0, 0, 0. Right? So now this has become like a diagonal detector. Right? By combining two filters, I somehow came up with this number. Or maybe this is not even necessary. There is some F3 sitting here, which is actually doing this job. We don't know that. That is the black box of the neural network. That's what happens during training. So now what we have done, we have taken the power of the neural networks and we have thrown in convolutions into the mix. So now it is convolving, but the weights are not single weights, but they are filters. So it is learning a combination of numbers which will represent the feature. So now this part, this manual feature extraction, this has gone in CNNs. Why? Because all we are telling us, I need to represent this image using like 15 filters. You come up with the correct combination. Right? And if 15 filters are not enough, take 30. I know, do 30. If one layer is not enough, take 5 layers. Because by this time, we can solve the deep learning problem. We have a lot of algorithms, a lot of methods, which will really address the problems with deep learning, the gradient descent, vanishing gradients, all these exploding gradients, all these we know how to solve by this time, right? So we are willing to go deeper, and instead of giving a single filter or a single node, we are converting the node into a filter. Where is a combination of numbers? We are hoping that it will actually do convolution. Right? So our primary approach has changed, where we are not telling so our primary approach has changed, where we are not doing this anymore, where we are not doing what ANNs did. We are not doing this anymore. We are not saying find out how each pixel is related to every other pixel in the image. Okay, what we are telling instead is find the correct convolution which will represent this diagonal of bright pixels. Now, as a result of this, every pixel need not actually talk to every other pixel. Or every other pixel. So we do not have 19608 combinations. We only have the number of filters weights, right? The number of weights which is present in the filters, that is our number of parameters. Of course, times the number of filters in the hidden layer. So since now we have also reduced the dense connection problem, right? We are not telling, okay, network, see how each pixel is related to every other pixel. We are telling the network, here's a blank canvas, you do convolution, find the correct combination of numbers within this filter, which will represent a useful feature. We are not even telling which feature. We are just telling find the useful features. That's all. You got the idea?
Professor,
Yeah.
so you have talked about doing backpropagation to update the weights of the filter instead
Yeah.
of the neuron itself.
Uh,
So my question is, how can we populate the correct weight into particular field of the filter? Because they have maybe 9 or 16 or 4 weights in each filter now. So
Yes.
how backpropagation is performing that exactly during
Yes.
tuning?
Correct. So the number of weights, I mean, the filter size is a hyperparameter which we will declare. So we will say, represent, do a 3 by 3 filter or 5 by 5 filter, 12, 11 by 11, whatever. We will give that number, but the actual numbers which go into the filter, like these one, like this combination, that is learned during training. Similar to how weights are updated in a regular neural network. Now, forget that this is a neural CNN for a minute and see how in regular neural network weights are updated. This is W1. So this is W1, this is W2, W3, up until W9, right? That is exactly what is happening in CNNs as well. The weight updation, the back propagation, everything is very similar to what we have already done in neural networks. But here it is learning the combination of numbers.
So
Right?
the form is because the direction is actually reverse. Because in the forward pass, I can make the answer simply by summation, right? So how can I backpropagate the summation result to back to W1 to W9? That is my answer. That is my question. Yeah.
Okay. So you are asking,
Yeah,
you are asking how
the
does
backpropagation. Yeah, the
yeah, yeah,
backpropagation.
correct. Uh, why is that a problem? I don't understand. I mean, this is still what your basic logistic regression did, right? So even there, we had W1 times feature 1 plus W2 feature 2 and all that, right? And then there was a bias term. So this is in a way very similar to what we have already done. The way, so the instead of the denominator being, okay, I think I understand. So instead of the denominator being output by weight 15, just that this weight 15 is now sitting inside a filter somehow, right? So this is the output. Okay, this is the output, and this weight is, if you take a regular neural network, for example, okay, this is weight 15. Okay, this is my output. This guy is connected to this. Let's say this guy is connected to some weight 6. Okay, and this is connected to, let us say, weight 2. Okay, So in basically a densely connected network, we are doing weight 15 is related to weight 6 times weight 2. So we are using the chain rule to find out how much of this update is going to result in an error here. Okay, and this is going to be the error at output. Okay, now same situation, we are just considering within the neural network. Okay, let us say this is weight 2. Okay, and this is weight 6, except that this is now sitting inside a filter. That is the only difference. This is, let us say, weight 15. At the core of it, the operation still remains the same, except now the weight is actually sitting inside the filter.
Yeah, I somehow got your meaning. Is we use the same analogies that we do traditionally based on chain rule methodology, but
Yeah,
now we organize all the weights in a form of grid.
exactly. So we are just putting the weights inside a filter. That's all.
All right, got it. Thank you. Thank you very much.
Okay. So what did we achieve through this convolution operation? We converted our filters as weights. So effectively, we are introducing a local connection instead of a dense connection. In my CNNs, every pixel in my hidden layer was connected to every other pixel in my, every other feature in my previous layer, right? But when I use a 3 by 3 filter, okay, and when I convolve it on an image like this, at any point, it is only talking to 9 pixels at a time, right? So it is not actually fully connected. It's not densely connected, okay? It is only talking to a very localized, very small portion of my image. If the same were a dense filter, a dense connection, I would have 9 weights to update. But since my filter here is a 2 by 2 filter, 1, 0, 0, 1, I have only 4. So suddenly, from if my image is 256 times 3, instead of the ridiculous 1 million or 100 196 200,000 numbers that we had, right? It was around 200,000 approximately. Depending on the filter size, this number will be even one third or half or one third, or depending on what filter size that I'm using. You see the advantage, right? My filter is only talking to a very small portion of the image at a time, and all the other weights are inferred to be 0. That's why you see these zeros. Because those zeros are, it is like a dense connection where all the irrelevant weights have now been constrained to 0. Because we feel, it's not necessary to find all these global connections. I'll talk to just one portion of the image and then move to the other portion, and keep going on it. Is this point clear? That's what happens inside CNNs. Okay. It's very quiet today. Am I going too fast or should I slow down? What happened?
I think it's clear that the advantage. I think we see the advantage for sure. Less computing power, all those things kick in here, right?
That's the thing with the online class, right? So there are a lot of non-verbal cues in a regular session. So uh, this is typically the point when the class like kind of the face lights up because they can actually see the advantage of CNNs. This is like the light bulb moment. But of course, I can't see that in the online session, so I have to really get feedback from you guys. And secondly, the weights are shared. What I mean by weights are shared is, you see, a filter is not going to be learned unless it is consistent. It is consistently useful, right? Let us say there is a cat, and there is this some whisker feature, right? There is some filter which actually detects this in different orientations, right? Now, if I want to do a cat dog classification, this feature should appear consistently in multiple locations of the image across all images for a filter to actually pick it up, right? So it is not that there is this particular filter which is useful in one part of the image, or in a very specific case. Only if instead of calling weights are shared, I'll change it slightly and I'll say only shared weights are learned, right? Manually, if I'm going to pick up some features like an eyebrow detector or the distance between two eyebrows, if I'm going to change my perspective a little bit like this, the algorithm fails, right? Because I'm focusing too much on a particular feature which I feel is important. But when the neural network learns it, we remember we are not doing any manual feature engineering. Only shared weights are picked by the network. So it can reuse a filter multiple times across different locations, right? So if it's going to pick up an edge detector, if it's going to pick up an edge detector, something like this edge detector is not specific to the corner of an image. Edges can appear anywhere, right? It can appear in the center, in the corners, in different locations. So it can use the same filter in multiple locations of my input image for different input images. So a weight is very precious, and it is learned across multiple from looking at multiple images. So in that sense, a filter is shared actually. It is shared over multiple locations in the image. Did the second point make sense? The first, we converted filters as weights. I mean, we converted weights to filters, and inside the filters, there are actually weights which are changing. And even that, it is shared. Why? Because I can reuse it. these two are traditionally the most famous advantages of CNNs over ANNs. Okay, can I go on?
Yes, Professor. Sorry.
Yeah, please go ahead.
I think that it's just like I think we get. I maybe it's just me. I get like the whole general ideas, but maybe because of one of the terminologies that introduced today a lot, that's why it gets a bit like we try to catch up. So it's the node, and then can you give quick no, like quick definition again so that we can connect all of the dots from like node to filters to features, then we understand wage. Yeah.
Okay.
Thank
Okay.
you.
So
Let's do some of this. Thank you.
sure. Okay. So node, okay, is still I'm going to still define a neural network using input and hidden layers and output. Okay. So a node is still going to be something that resides inside my hidden layer. But in CNN, a node has become a filter. So instead of this being like a circle, it's not this anymore, it is this.
Okay.
Okay.
Yeah.
So the each node is now a filter.
So one kernel is the feature. That's what it's called.
Yes. So filter or kernel.
Got it.
Okay. And that is going to pick up, it's going to pick features. It's going to pick features from my input image. I'm going to use this to detect edges, for example. The edge is a feature. I mean, feature can be anything. It can be we don't know what neural network is doing inside. It can even find the cuteness of the cat, right? It can find the ear orientation. It can find the nose shape of the nose. We don't know what feature it is picking, but we are sure that it is picking some features. What it is picking from the image is actually the feature, which is basically the traditional definition of feature actually. Whatever we called feature before, like in traditional ML, like date is a feature, right? Because date helps us identify, predict the output variable. So if I have to convert this to raw ML terms, a feature is something that is going to help me predict that an image is a cat. It's an image of a cat. Except I'm not doing it. I'm letting the network pick these features by using the kernel or the filter at each node.
Yes, and one of the features has to be in numbers, right? Or it like what it means is like it has to translate it to numbers in order to for machine to understand, right?
When we talk about CNS, we don't go there. As long as we are doing traditional ML, of course, yes. It has to translate to a number. Like I have to give like an edge detection score, like a right score, like right edge detection score, left detection score, a eyebrow score, a whisker score, right? As examples, right? As a whisker score, a mouth score, but we don't know what the neural network is basically doing.
Got it. Can you quickly explain again why it's called edge again? I understand edge, but suddenly forgot. Edge
Okay, so
detection. Yeah.
yeah, edge detection is basically so what really differentiates and says that something is present in the image as compared to there is nothing in the image, right? It is this systematic variation between the background and the foreground. And it is this line which basically defines an object. Okay, that is the edge.
Thank you.
Okay, so
Yeah,
yeah.
I had a question. So technically here what we do is like a pixel has relevance around its surrounding to make a semantic meaning of it. So because of that, we are trying to create, instead of a point weight, we are trying to create a two-dimensional array weight. And that be the right understanding out of it.
Correct. Correct. So instead of giving a single number,
Uh-huh.
we are giving as a two dimension. Why?
Mm,
Because we know that convolution works.
mm, mm. Now, if I am extending it to a three-dimensional object detection, so should I have to add one more dimension? For example, like I am trying to do something for a asteroid detection or something. So then that model would require another dimension to get added so that it can perceive an upcoming or approaching asteroid.
Uh, yes. Yes. Yeah. The short answer is yes. I mean, the basic approach is basically going to remain the same. Convolution is going to be the core operation. But if your image by nature is going to be 3D, then we will not have. I mean, this is actually a 3D, right? We say it's 2D, but it's actually stacked. The red is behind the green, and then there's blue, right? But if you want to add more dimensions, then of course you will do a 256 by 256 by n. The n being the number of dimensions that you want to give. Yeah.
Now, if CNN is a solution for the 2D, and now we manage with the 2D to process RGB or YUV images, and now
It is always RGB. It's not YUV. YUV, all these other formats, the system, the other color display systems, they understand. But if it goes to a CNN, it's always RGB. It
RGB.
assumes that the images is going to be the first dimension is red, next is green, next is blue.
Sure, sure. So now, if we look at the
That
time,
1 minute.
sure.
That well, technically, I'm not sure if the neural network would really care as long as it's getting like a 3 layer or 2 layer or 1 layer. As long as we define things properly, I think the neural network will not care if it's an RGB or YUV image. But representationally, it's easy to get the features well defined in an RGB image than in other formats. So people generally prefer RGB unless there is an explicit advantage to representing an image in YUV or whatever the other formats are.
Thanks, understood, Professor. So
Yeah,
if
move on to your question.
for example, like you were showing one of the image in different colors in the previous session, and like if we are detecting some of the edges for perhaps in all the three different colors, one is with R, one is with G, and one is with B, and now finally it has to be clubbed, the independent edges detected in all those three colors have to be clubbed with the algorithm in some way, and the CNN by nature, it doesn't give a means to club the multicolor arrays. Is that correct?
So here is where it is slightly we have to really imagine these things. Okay.
Okay.
So what happens in ANN is basically I said that an ANN is trying to make sense of the relationship one pixel what it has with other pixels. Now, if it's a 3D image, remember there's going to be another layer here, which is basically probably 156, 150, 140. And for simplicity, I'm going to just have 258, something like this. It is also finding the relation because it's densely connected, remember? Okay. It is finding, or there is a second layer, some neuron here, sitting here, which is finding how there is a relationship between this 200 and this 156. This 200 and 0. This 200 and 0. Apart at the same time that it is finding a relationship between 220, 200 and this 0. This guy sitting right here, since it's fully connected and we have spread it out like this, right? That's called flattening, by the way. So since we have flattened it like this 200 is here, this 0, 0, and somewhere down the line, we have this 156, and then we have 0, 0. Now this one, which gets input from everything, it is actually trying to make sense of this combination of, how the first pixel is related to the first green and the first blue as well. So in a way, it is actually looking at all these things together. Right? You got that? Now, if you go to the CNNs, the CNN is also doing exactly the same thing. It is fine. It is in the first layer, it is creating this kernel, right? In the second layer, it is operating, let us say this is the R. This title is monochromatic. When you look at the nodes,
what you're saying,
don't get
like
confused.
the channels are not completely independently processed. There are interconnections exist across the channels.
Somewhere down the line. In the first layer, it's probably not there. That's what I'm trying to tell here.
Okay. At the later layers, like it gets combined. Understood.
Yes.
Okay. Now, Professor, so when we want the two-dimensional images to process the third dimension, so the information is being fused at the later layers.
Correct.
Now, if I have more and more dimensions, for example, I have a X-ray dimension, I have a time dimension, I have a gravity dimension, and all those things. Now it becomes hierarchically, multiple stages of fusion. Is it correct? Or
Correct.
okay, and it cannot be dealt at multiple dimensions, but rather than it has to be dealt as multiple layers, which gets fused at some point.
Yes. That's why there are these deep layers, right? The job of the deep layer is to find all these complex patterns.
Okay. And when we do this multimodal fusion, technically we adapt such, these days, like we have the model which takes the text, image, audio, everything and integrate it together and, tries to find out. So in that case, like what we do is like we have independent channels and finally it gets fused together. Is that correct understanding?
That is a whole beast altogether. The multimodal. You remember we discussed transformers in the previous session, right?
Yes.
Touched upon transformers when we did texting. So that is a whole different approach to solving vision problems. Now we are talking about CNNs. There is a whole beast called vision transformers, which actually converts a computer vision problem into an embedding problem. Okay, so that way, all these translation that becomes easier because that is the core strength of transformers, right?
Yes. And the whatever we use the transformer for the NLP, that cannot be as it is used. It needs a certain customization when it has to be used for vision.
Correct. They are called VATs, vision
Okay.
transformers.
Okay. Thanks, Professor. Thank you.
Professor,
Okay.
I have a
Yeah,
question here.
sure.
Uh, I don't know if you know of this game called Roblox.
Yeah, my son plays it.
So,
Yeah.
so my question is, this year we heard earlier this year we heard a lot of Roblox trying to use the AI tech. Not just listening into all this discussion, I was wondering if CNN is behind all that.
Uh,
When they create all these different,
Depends on what they are trying to solve, right? Really.
okay,
So
because
I talk very highly of CNN because the module today's session is CNN, but it
Mhm.
is kind of outdated.
Okay,
The latest are the technology that I just talked about, vision transformers.
mhm.
That is supposed to be the state of the art. But again, that doesn't mean that CNNs are not useful. Still, for a lot of basic tasks, CNNs are extremely popular, extremely powerful, incredibly powerful. Okay.
Okay,
So, since VATs are vision transformers are already in the game, it's very problem specific. Vision, it's not that all the vision problems are solved using CNNs.
oh, okay,
So it could be vision transformers as well.
okay. Thank you. This is just an intriguing question that came to my mind. Thank you very much. Yeah.
Sure, sure, sure.
Yeah.
Doctor, one question, please. Just as a differentiation between the ANN and CNN, can we say the CNN is a special type of ANN or in a more
Yeah, you
intelligence?
can actually,
Mm,
yeah, you can really say that. Yeah. CNN, you can say it's a variation of your AND.
okay, thank you.
Okay. So if we have, all right. So what we get out of a convolution, we are not just going to call it, we are going to come up with a special name for it. Because remember, and I think that this circles back to, I think, Fluent's question. No, we just came up with a lot of names, right? So we have to come up with one more name. The output of an the output of a filter after convolution is going to be called a convolution map. Is going to be called a convolution map or a feature map. Okay, so let's say I have an image, I have a filter. Whatever I get out of, or whatever I get after convolution is going to be called a convolution map or a feature map. Remember, in previous variations, after the output of the first hidden layer was only a single number, right? Where the spatial arrangement was not very important. But since we have evolved the operation, we are going to come up with a new terminology as well. Okay, the output of a convolution is going to be called an activation map, convolution map, or feature map, or activation map. People again use these terms interchangeably, but it all means the same. It is the output of the convolution operation. The output of the convolution operation is going to be called the feature map or the activation map. Okay, we have discussed this slide. I'll give you a couple of minutes to go through this and see if you have anything to ask. Otherwise, we can take a break at this point. So can we take a break now and join back in 7 minutes? I leave the slide on the screen. If you have any questions, please ask. We can start with whatever questions you might have.
Professor, one question.
Yeah.
This activation function, I mean, there used to be an activation layer also, right, in the convolutional functions? Or it is only the filters?
And activation layer. Not sure what you mean. We'll discuss some hyperparameters now. Let's see if
Okay.
that comes up during the session.
Sure. Okay. But otherwise, like technically, the CNN methodology is like it's a set of kernels and filters, right?
Correct. That's yes.
Okay. Fine. Thanks.
All right. Let's start with the break. I'm going to be away for a few minutes. All right, let's continue. So we've discussed this part of convolution. Now, since we have is everyone back? Can you give me a thumbs up or something? Is everyone back?
We're here.
Thank you. Okay. So what we are going to do in when we build a CNN is basically since we have now added a little bit of what is it, complexity, we are going to take some mitigation efforts for that. We are going to introduce something called a pooling layer. Okay. So what pooling layer basically does is um, the pooling layer finds the most important you know part of a given area in a convolution map. Like for example, if this is the result of a convolution, let us say, okay, this is what my filter one has given. This is the output. Okay, so by doing a pooling operation, and what I'm doing here is what's called a 2 by 2 pooling. So when I say 2 by 2 pooling, I am basically finding the most important information within this 2 by 2 area. So I will now retain 120 and leave out all the other numbers, right? And here, if I do like a max pooling for this 2 by 2 area, the max number is 80. Okay, so this is 198, and here it will be 78. So basically, what I've done here within this whole feature map, I've picked out the most important four numbers that are required to represent this feature map effectively. Right? Uh, Before we do this, let us do something here, or we'll come to that later. Okay, so pooling is a common operation which is used to reduce the size of my input to the next layer. Now, what happens is instead of the H2 getting this input, okay, it is now going to get this input. Now I have reduced the 4 by 4 input to a 2 by 2 input, which is again is going to be computationally very efficient. Most common pooling operation is what's called max pooling, where I retain the maximum number within a given area. Again, this 2 by 2 is a hyperparameter that I can pick. I can do a 2 by 2 pooling, or I can do an 3 by 3, 5 by 5. So that's basically n by n, where n is a hyperparameter that I'm going to pick. If you're going to pick a wide area, then a lot of information is lost. If I'm going to pick a small area, it is still efficient, but a lot of information is retained. Okay. The disadvantage with pooling is basically so I'm reducing a four number array into a single number, right? Which is so the pixel, the feature information at these locations is going to be lost, but I'm willing to pay the price for computation. I'm hoping that future layers in future new filters in other hidden layers will basically make up for this loss in information. Okay. Did you understand the pooling operation and why pooling is important?
No. How did you select the 120, 80, and put them in the 4 cells
That's
of the
that's just the maximum number. That's why it's max pooling.
max pooling? Okay.
Within a given grid, pick the max number. People
All right.
usually don't
Thank you.
use min pooling, it is only theoretical. Average pooling is slightly more popular, but the most popular is probably the max pooling. If I do an average
Okay.
pooling, I would have the average of these four numbers here.
Thank you.
Sorry. So for the 2 by 2 on the right, you picked 120 and 190 is the max, and then the second column would be the minimum. Sorry, how do
No,
you come up with this two again?
with this 80.
Yeah.
So I do this grid and then I move to the next grid. This grid.
Oh, so the pooling is like if it's 2 by 2, then you pick out like two numbers and
Oh
then
no. So this is I did introduce the concept, but it's there. This is 2 by 2 with what is called stride 1. So stride is how I am going to stride 2. How I am going to move to the next pixel. Now a couple of things I can do. 2 by 2 is the area over which I am going to pool. Okay. So if I am going to consider this grid as my next grid, like this grid, okay, then it is still a 2 by 2 pooling, but now it's going to be 120 and the maximum number here is 111. And then I will go to the next one, in which case it would be 80. And then I'd come down over this area, okay, that would be 198. And then move to here. Again, the same sliding operation that we did before, 198, right? And the last would be 67. And I would move down, come to this 2 by 2 grid. Again, 198 is the max number. And again, 198 is the max number here. And move to the last grid, which would be 78. So this is still 2 by 2 pooling. Okay, 2 by 2 pooling over the entire image, but with stride 1, where I'm just moving to the next position within the image. Now, if you look at this, there's a lot of this 198 which is coming up, right? So what people thought was, I know that 198 is important, so why don't I just skip one column and go to the next column? Like start here. Okay. So I start here and instead of in my next operation coming to this 2 by 2 area, I'll skip one column and I will go here. And similarly in my row, I'll skip this row. I'll skip this row and I will go here. Again skip this column to go here. So now the result of this is this 2 by 2 grid. Okay, so now what I have done is basically I have reduced this 198 appearing multiple times. So within my first 2 by 2 area, 120 is the most important number. And I'm just cutting, now moving to the next important area and retaining 80. Now all these four numbers are present here as well in this matrix as well. Right? 80 is here. Sorry, 80 is here. 120 is here. 198 is all over everywhere, and then there is 78. The same information is captured here. So instead of just moving to the next column, I'm skipping one column and I'm doing here. That is the hyperparameter called stride. We'll talk about that in a minute. But the 2 by 2 here, it basically refers to the area over which I'm pulling rather than the end matrix size that I want.
Thank you. So and you can do 2 by 2 and then 3 by 3 or 4 by 4.
Yes.
Sorry, why is it important again?
Yes. So let us say I do a 4 by 4 pulling over the whole image. What will be the number? I'll just have one number, 198, right? If I do a 4 by 4 pulling, it will give me just one number, 188. Why? Because that is the most important number. That's the max number.
Yep.
We do a max pull. Now, I've lost a lot of other important big numbers here, right? Like 120, 111, and this 89 and all that. So I want to have a sensible number which will which will give me the computational advantage, but which will also retain enough information in the image. That's how I come up with the pooling size.
And 2 by 2 is currently the optimal one.
For this image. If you take a
Yeah.
256 image or 1000 by 1000 image, 2 by 2 is much
small.
too small. Yeah.
And sorry, why is max pooling is often better than min pooling?
So min pooling nobody uses, just theoretical, right? So what I want to achieve through this pooling operation is, remember why we did convolution, right? If that particular feature is there in the image, we will get a big score, right? So we want to retain that score. We want to say that, okay, there is an edge which is present in this part of the image. That is all I need to know through my convolution.
And so I think I missed the first slide. Sorry, I came in a bit late. But this pooling method is the same thing. It's like one type of the kernel convolution, right?
No, so
when you say kernel,
convolution,
you mean times and then plus, like sum up.
yes,
But this is one
the
type
dot
of
product.
convolution.
This is not convolution. There is no computation happening here. It is just picking out the biggest number within a given grid. That's all. There's no computation happening.
Yes.
So this is the second stack. So the first stack is going to be a couple of hidden layers. So we are going to have input. Okay. We are going to have input, and then we have hidden layer 1, and then pooling layer 1, and then hidden layer 2, and then pooling layer 2, like that. So the output of hidden layer is the input for my pooling layer. Now the output of this pooling layer will be the input for this hidden layer. Now, if I have this 4 by 4 image as the output here, right? This is my 4 by 4. My 4 by 4. Now, this whole 4 by 4 would go as input to H2 traditionally. But by introducing my first pooling layer, I am reducing this to 2 by 2. So the job for the H2 becomes easier.
Yes. Sorry, I missed this slide. Thank you.
Okay. So a number of
Sorry, Prof. Just to ask, is it by a matter of principle that we usually don't overlap for pooling? So if it's a 2 by 2, you choose strike 2, compared to
No,
strike one because it will create what you created just now, having so many 198s.
yeah. So again, we may come to the hyperparameter. We have the slide just right here.
Okay.
Yeah, we'll come to that. Okay. So a couple of more hyperparameters that we are going to discuss in CNS. This is in addition to the hyperparameter that we already know. The optimizer, regularizer, all the hyperparameters, the number of layers, number of neurons in a hidden layer, in this case, number of filters. Okay, so apart from that, we are going to discuss all the other extra hyperparameters specific to CNS. The first is the size of the filter, right? Again, it's completely in our hands. Do we want to do a 2 by 2 filter or a 5 by 5 filter or a 10 by 10 or 11 by 11? So the filter size is going to be something that we can actually design. Okay. Now, how do we come up with a good filter size? Any thoughts on this?
Maybe like proportionally to the size of the big thing.
Size of
The size of the data
size of the image, right?
image.
Correct.
Yeah.
Exactly. So if we have a 200 by 200 image, okay, if we have 200 rows and 200 columns, and if we do a 3 by 3 filter, it also depends on what features are there. Remember, if I'm going to have like a tiny whisker of a cat, okay, and if I am going to have a filter that is so big, okay, remember there are other things going on within this image as well, apart from the whisker. Okay, so within all this noise, if my filter is too big, it might actually miss the important identifiable feature or the differentiating feature of the image, right? If for the same whisker, if I'm going to have a smaller filter size, okay, in the first pass, it's going to pass through some portion of this whisker, and then second time it's going to come here, third time it's going to come here. So it is consistently seeing that particular shape appear in the image, right? So the size of the filter should make sense. It should be small enough to pick some intricate details in the image, right? But it should not be so small that it really negates the advantage of CNE, right? If for the same 200, for the same 3 by 3 filter, if the image size is going to be 1000 by 1000 pixels, okay, that's going to be very tiny. Like this is my whisker, let us say, and this will be my filter size, right? So it's going to be so painstaking that the computational advantage of my CNN doesn't work anymore, right? So for probably 1000 by 1000 image, we can really start with like a 25 by 25 filter. I don't, right? So that is completely dependent on the size of the input image and also the kind of feature that we want to pick. The usual thing to remember is if we want to pick some intricate details, fine details, go for a smaller filter. If you want to pick out like features which really stand out at a glance, you can find it, right? Then we can go for bigger filters. In medical images, let us say there is a very small, lesion or something that you want to find out. Small filter would make sense. There is a product line and you want to find out if the product is damaged at some point. You want to find, very even minute damages, go for smaller filters. right? You want to do a generalized identification. Is there a face in the image or there is no face in the image? You don't need really intricate features for that. Probably you can work with a bigger filter, right? Very problem specific and image data specific. Um, the depth. So what I mean by depth is the actual number of filters that I'm going to use. What we used to call number of neurons in the hidden layer in our ANN. This is the equivalent of number of neurons. So if I have like 6 filters, then okay, I hope you can understand the image. This 6 rows, 6 columns, three. Three is RGB, right? And I have 2 filters, two 3 by 3 filters. But each filter is acting on the red, green, blue component, right? So each filter is into 3, right? So my filter 1 is 3 into 3, 3 by 3. Filter 2 is 3 by 3. This 3 by 3 is just this. But since the image is 3-dimensional, each filter is working on the red part, the green part, and the blue part. That's why this 3 is important. This is the RGB layer. Okay, so each filter is going to give a 4 by 4 size activation map or a feature map that becomes into 3 again. At the end of my first hidden layer, this is going to be the depth of my output. So I'm going to have 6 4 by 4 activation maps. So the depth is another hyperparameter, which is basically the number of filters. Did that make sense?
Would you repeat that again?
So in my first hidden layer, H1, I have 2 filters, each of size 3 by 3. Filter 1 is 3 by 3, filter 2 is 3 by 3. Since my input image is an RGB image, there is a red layer, there is a green layer, and a blue layer. Each filter acts on each of these layers, right? So, as a result of that, I'm going to have 3 by 3 times 3 filters. For my F1, the same thing is going to happen for my F2, for the 2 filters. Each filter is going to give a 4 by 4 activation map, right? And that becomes into 3 because it is acting on each of this RGB layer. The RGB confusion ends with the first hidden layer. From second hidden layer, it is going to be the 6 activation maps, each of size 4 by 4, which is going to go as input to my H2 or my pooling layer,
Right.
P1 or
Okay.
H2.
Thanks.
Okay?
Sorry, how can you go from 3 to 4 again?
Hmm.
Like 3 times 3,
So,
and then this is 4 times 4.
So if I convolve a 3 by 3 over a 6 by 6, the resulting size will be 4 by 4. There is a way to actually calculate this, but for now, I'm going to, in modern slang, I'm going to ask you to trust me, bro.
Okay.
There's there is a formula for this. We will discuss that in a while.
And then the 4 by 4 is BSYN output. So it's called activation map.
Correct. Yeah.
Thank you. And the first one would be the data. And then
Correct.
and then the second one is the features. And actually that the whole
Filters.
preset is the filters. And
Correct.
each of them is features. And then 4 by 4 and activation map. Thank you.
Activation. Exactly. Correct. So, yeah. Okay. The next hyperparameter is a stride. We briefly discussed this. Um, But sometimes, like when we do the convolution, sometimes we don't really have to go to the immediate next column. We can choose to skip one or two columns in between, and that is the stride. Again, it depends on what fine features you want to pick out from the image. If we want to pick really fine details, then we have to stick with stride of one, which is default. Stride one means go to the immediate next feature, next location. This will be stride one. Okay, so stride one, and stride two will be if I skip this and if I go here. Okay, and from here I go here. Similarly, in the row, I'm going to go from here to here and here to here. That would be stride 2. Okay, what happens if we have such a big, well, like if the stride is too big, we might miss out an important feature which is actually lying over here. If there is some feature here, we didn't even consider that during our convolution, right? So we might actually miss it completely. If we always default to stride one, then remember for 1,000 by 1,000 image, huge image, we are just going very, very slowly, which would be very redundant. Okay, so higher stride would produce smaller output volume. Bigger stride would produce smaller output volume. Smaller stride would produce bigger output volume. In the case of filter size, a small filter will increase the size of my activation map. A big filter will reduce the size of my activation map. Okay, consistently in all of our operations, we kind of started with this position, right? Which means that anything which is present in this part of the image, you know, I'll explain this in a minute, in a slightly different way. Okay, let us say that I start with a 2 by 2 or a 3 by 3 filter. I start here and I cover this whole area in my first convolution operation, right? This particular pixel, I'm seeing it once. And then I'm going to the next with a stride one. Again, I'm covering a different area this time. Okay, I'm covering this area. Again, I'm seeing this particular pixel twice. And then I'm going here, and then I'm go on. And then when I come to the row, when I come to the next row, I'm again looking at this particular pixel, which is 3 times. Okay. If I move to the next location, this pixel, again, I'm looking at it for the 4th time. The same pixel, I'm seeing 4 times. But consider this pixel where I'm starting from. In my first convolution, I'm looking at this pixel once, okay, once, and then okay, looking at this once, and then next time I leave this pixel and then I go to the next one, I'm covering this area. Okay, and when I start the next row, I start over here, right? So I'm only actually looking at this pixel only once, which sometimes is not important enough. Okay, so if there's anything important lying here, I'm not getting I'm not picking out an important feature which might be present in that corner of the image. Or in other words, if in my traditional convolution operation, the corner pixels are kind of ignored. Okay, so what I would do is, I would do a zero padding where I would slightly increase the size of the image. Okay, and I would pad these areas with zero values. That way, my first convolution operation will happen over this area, this 3 by 3, not this 3 by 3. Right? So the corner pixels are given equal importance as any other pixel within my image. So that zero padding, if we want to do a zero padding or not, is again another hyperparameter that we can actually play with. Any questions still here?
How often do you do the zero padding? Do you always
Kind
do it?
of, yeah, kind of like default. If especially when the image has features which could be present anywhere within the image, right? So we kind of default to a zero padding. So if you do zero padding, obviously your feature map is going to get bigger, right? It is going to be computationally a little bit less advantageous, but we will pick out the best features for it.
And you only put one layer of zero padding, right? That means it's only one row of zeros or one column of zeros. Or it depends.
Yeah. Again, it depends. You can also put like a two zeros. That again depends on the filter size, right? So if I have a 5 by 5 filter, this is a 3 by 3 filter, right? If I have like 10 by 10 filter, I should add correspondingly that many zero padding. That's why it's the hyperparameter. Linked to probably the size of the filter.
Yeah, I understand. What I mean is like the row. So one row and one column of.
No, it need not be. That's what I'm telling. So if I have a 10 by 10 filter, the image is probably, 200, 256 or something. The 10 by 10 filter will still only cover this part of the image, right? In its first operation. What if I want to do this using the 10 by 10 filter? Then I will add correspondingly that many zeros, zero
Oh.
padding. It depends on what I want to achieve through the zero padding, right?
Thank you.
Okay. So we saw hierarchical representation when we did ANNs. And we kind of said as we go deeper, we're just coming up with more and more complex shapes and more complex equations to higher powers, and it just figures it out. But what happens inside a CNN? Surprisingly, something very, very similar. So the low level features, again, we are going to be a lot of terms today, I know that. A low level feature is basically the result of early layers. Okay. Early layer output, we are going to call low level features, or within your neural network, the early layers are going to be the low level features. Mid level and high level as you go deeper. As you go deeper into the neural network. Okay, so we show, let's say, for to the neural network, we show the image of this car, and then we say, find out the most repeated pattern. So it would come up with these things. As you can see here, these are very similar to the edge detectors that we discussed, right? Lines of different orientation. Now, these lines of different orientations, they are combined to give little bit more complex shapes. You can see some things emerging, but you still can't like name it. You can't give any specific name to all of these. But these mid-level features, they are combined probably at the nth hidden layer, 10th, 12th, 15th, whatever hidden layer. And now you can see some really nice shapes emerging from this, right? You can see some radial spoke-like things. We can see something like a window pane. We can see something like, grass or something. We can see the curves of the tires, of the wheels, right? Some steering. So again, the radial arrangement of the cars. So as you can see here, the more complex shapes, they emerge as we go deeper and deeper into the neural network. So at this point, again, if we map back to our machine learning, this is exactly what we wanted, right? We created mathematical formulas to do this. And once we had this, we had a layer of ML, SVM or something, which combined all these things to give an output. Here also, in most CNNs, there's going to be a final layer of fully connected network. Fully connected network, which will basically combine all these individual features, and it will do like a traditional ANN there. Okay, so the CNN picks out the features. The trainable classifier, it can be an ANN or it can be an SVM or it can be some random forest or something. Okay, the trainable classifier is basically anything that uses these features to build a model. So any CNN is going to have these two components. First couple of CNN layers, followed by a fully connected layer where actually the classification is going to happen. Right? So what we achieve through CNN, you see how people from different disciplines, they came together and they came up with these formulae to do feature extraction. We outsourced that feature extraction to CNNs. Okay. Through the extracted feature, we built a model basically. And that's how things got really useful.
Sorry, may I see the slide again? Between, yes, traditional machine learning. So you do so sorry. I think I might have get it, but I'm not getting it fully. So the CNN here is when you extract features, um, but the traditional ML is the ANN.
No. So this is the traditional approach, and
Yeah.
this is
The
the
deep learning.
CNN.
Yeah.
Yeah, correct. So the deep learning methodology workflow is something like this. Again, we have the input. I've broken down this whole blue box into two smaller boxes. A first set of layers which extract the features, a second set of layers which actually do the classification.
Oh, so it combined the whole thing here.
Yeah.
And got it. Can I go back to one more slide? And what is the most important thing we should get from this slide, Professor?
The most important thing that we want to get from here is how the features are arranged within the CNN. In the early layers, very simple features are extracted, but as you go deeper into the network, those simple features they are combined in more and more complex forms to give preliminary shapes which actually define the data set.
Mm-hmm. And
Okay. Yeah.
and this
So
is
within
automatically.
correct, exactly. We didn't do anything. So in a cat versus dog data set, this might be just two eyes. This might be ears. This might be whiskers. This might be the dog's, floppy ears. So something like that. That's going to be represented. The whole data set is going to be represented.
Mm-hmm.
And all this happened because of CNN, because we chose the filters intelligently. Okay. Any questions? Papanchu,
So, Professor, I have a question. As you mentioned, the CNN itself is actually a black box somehow. We cannot fully explain what happened inside, but actually it works well by picking the features. Just in case we select a right size of filter, and also the hyperparameter, etc. Right?
Yeah, correct. Yeah. So as you can see, the title of this paper here, it says feature visualization in convolutional network trained from ImageNet dataset. So I mean, there is a way to go back and see what each layer is doing. But remember the kind of things that we are going to doing inside a CNN, right? Conversion by nature, there is a lot of loss of information. On top of that, we are doing a pooling layer, right? Probably we are doing some sort of batch normalization as well. So all the numbers they get distorted once you do normalization. So you see the number of things that we add in a CNN, and it's really difficult to trace back and see really what's happening inside a CNN. But I mean, there are ways to do it. If people were able to do it in 2013, obviously in 2026 you can do it. But it's just hard, difficult.
So CNN is generally facing a common problem is it is hard to explain still because of the black box nature, right?
Correct. Yes. Not completely. There are lot of ways to explain, but but that just requires a lot of extra steps. If you just stop with CNN, if you show a working model to your, let us say, your investors, and you say, this is what my model is doing. Obviously, the next question is going to be, how did the model learn? You have to actually buy time, like a week or 10 days, and then come back with that answer to that question. So what I'm saying is, if you build a traditional ML model, you can actually explain. You can say, okay, these are the steps I did. This is the most important feature. I remove this column and the model fails. You can say that almost immediately. But that sort of thing doesn't happen with CNNs, with any ANN, with any neural network. You have to really buy time, go back, sit with the algorithm, do some extra steps, and then come with the answer. That's what people mean by non-explainability. And even then, it's not like 100% perfect. We are trying to reconstruct something using a lot of lost information. Why? Because by nature, convolution, pooling operation, normalization, by nature, you lose information.
I see, I see. So by nature, it is hard to explain from the deep dive because this is going to extract things from original with lossy algorithm.
Correct. Yes.
And another perspective I'm looking for is, as you've shown, there is a comparison to traditional ML flow that CNS is going to replace the feature engineering with the CNN methodologies. So my question is there any benchmark that we can choose CNN over the other, or in some cases, actually traditional MLs still wins in some scenarios? Could we have some benchmarking tools to
Yeah.
compare the two methods?
Yeah, definitely. So, I mean, if you look at the core solve problem that CNN is solving, it is a high cardinality, right? Like we reduce the 200,000 input data points to around 300 per uh, per data point, right? So wherever we feel that the data is high dimensional, high cardinal, uh, some nuanced features are present. Huge, humongous data set like million rows. Then actually CNNs work even for um, structured data, even for Excel sheet type data.
Got it, got it. Fully understand. Thank you.
Okay, so if you look at the concept, CNNs really the first successful CNN was in 1998, and this is the architecture. And the data set was MNIST data set. Input one convolution layer, one pool layer, another convolution, another pooling layer, and then a fully connected layer, and then an output layer, right? So this is a very simple architecture. So if CNNs were popular since 1998, then why didn't people really implement it until 2012, right? For all the other thing, for all the reasons that I mentioned in the previous session, like ANNs at one point, at that point, they had become really unpopular during the mid 90s, and that is called the another AI winter. Because although back propagation happened, still it was computationally very difficult to work with neural networks, right? Um, so people lost really their interest in neural networks, generally CNNs, until again in 2020. I mean in 2012, the winter finally ended, and I think what happened, what they did, we will look at it in tomorrow's session or the next theory session. we will combine this um, object detection and GANs in one lecture. Actually, GANs are really simple. Once you understand, it won't take more than half an hour. So the next theory session, we will finish images and then we'll move to LSTMs and RNNs and take reinforcement.
Yeah, Professor.
Yeah.
Where does NVIDIA comes in?
Correct. That's why CNN's one. AlexNet. So that
Here,
should be the core of the next session. Yeah.
2012?
NVIDIA.
Yes.
But if you mean GPU as a process, I mean as an inclusion in neural network, yes, 2012. Yes.
Wow. Thank you.
So it became anticlimactic. It should have given a spoiler alert actually. Any questions? Actually, we do have 2 minutes. I'll just quickly finish AlexNet and why it really won. Since we already have started discussing GPUs and NVIDIA and all that. Um, so since 1998, CNN's the first successful CNN was Lenet in 1998. It used youngest data set, successfully classified numbers. It was able to actually automatically read zip codes on mail, which was quite a big thing to do. It was trained on